Hi everyone, and welcome back to my channel, Floating Point Exception. Today we're going to continue sort of what I talked about last time, which is talking about the PCjr cartridges. More specifically, I was going to go into the details of the CRC algorithm and what I learned about how it works, and specifically how the PCjr implementation works. So hopefully you find that interesting. If you have other ideas, feel free to post them in the comments for other things you think I might do a good job of covering or just interested in. Anyway, without further ado, let's go over the details of the PCjr cartridges. Okay, so let's get into the details of the CRC, or Cyclic Redundancy Check. So what the CRC is an error detection technique using a polynomial similar to what you would use in linear algebra, but a little bit different of how it's used here on computers to make it a little bit easier. And it's just verifying that the data is corrupted. In particular here, this investigation was done to look into how the PCjr cartridges use them for checking to make sure it's a valid cartridge and that there's no issues with it. There are various different algorithms, direct, non-direct, different initial conditions, and reflected and reversed, which I'm not going to cover here. And the only other important thing to note here is the CRC is not an error correction scheme. It does nothing to give you any sort of indication of where the error is in the data, only that there is an error. For references, you can look at one of the ones online that goes over CRC algorithms in general is a Painless Guide to CRC Error Detection. It's fairly old, but a good overview of how this works. The file I found was crcv3.txt from 1993. There's also a CRC calculator online that I found useful for just playing around with and learning how it works. And specifically for the PCjr, you're going to want to look in the technical reference on page A106. That is where the BIOS CRC routine for the cartridges is. So the first thing to note is, what is the CRC polynomial? This is the main part that determines how the particular CRC algorithm is calculated. And it's not the same as a normal or linear algebra polynomial arithmetic. It just looks similar, and it is similar in a way, but not exactly. And in the computers, the CRC uses exclusive OR for all the math on this. So it's like addition and subtraction, but there's no carrying. So if you want to think of it that way, you'll see what I mean once we get started. Now for some examples, a 4-bit CRC for one nibble, or half a byte. You could have one that is x to the 4th plus x plus 1, or as just written out more simply, x4 plus x plus 1. The CRC order in this case is considered to be 4. That's the highest polynomial value here, which is x to the 4th. And it would be represented as 1, 0, 0, 1, 1. A lot of times you don't see this initial 1 because it really doesn't matter. That's the order. It's always considered to be there. So you might just see it as 0011 or 0x3 in hexadecimal, same thing. And an example of a 16-bit CRC, which is 2 bytes here, would be like x to the 16th plus x12 plus 5, x to the 5th plus 1, or 0x1021 in hexadecimal. There are plenty of other examples of what these values could be, although you can't just willy-nilly choose what values you want, or at least have one that works well. The text document that I referenced earlier actually goes into better detail over how these are chosen so that they work well. So here I was going to do an example of what's called a non-direct method, which means it's using augmentation, which I'll explain. Specifically, this is CRC4 ITU. The polynomial is the same one as before, 0x3 or 1,3 if you're including that leading 1 bit. And the message here we're going to do is, just as an example, is the ASCII left square bracket character, or 01011011 in binary. And with an initial value of just one of the nibble of 0xf, or just all ones. So if we're going to write this out kind of like long division, the polynomial is on the left side here, 10011. The initial value is this 1111. The actual message is 01011011. And then the augmentation, all that means is that you're adding on, in this case, a nibble of all zeros to the end of the message. So as I said, this is kind of be like long division, and we'll just go through this example quickly here. So what you do is, if this left digit that you're working on right now is a 1, then you pull the polynomial down and exclusive OR this, and you put a 1 up here. So you're doing 1 times the polynomial. You want to think of it like long division. And then you subtract it out, or in this case, exclusive OR. So again, we're going to ignore carries. So this just becomes exclusive OR 1 and 0 is 1, 1 and 0 is also 1, 1 and 1 is just 0, and 0 and 1 is 1, and then you pull down the 1 to get to the next digit. So that's how we get the 1 up there. If we continue, again, the leading digit was a 1. We pull the polynomial down, do the exclusive OR again, and we get exclusive OR 1 and 0 again is 1. 0 and 0 is also 0. 1 and 1 is also 0. 1 and 1 is 0. Pull down the 0, and we have the next sequence to work with. And if you continue with this, you'll continue to build your quotient up here, which is actually not the part we care about. The CRC is actually going to be the remainder. So here you can see we're starting to get into the augmented message, and we continue, and finally we have the last sequence. Oh, and I didn't give an example before of, like, for instance, if you have the leading digit here, or bit here as a 0, we're just going to exclusive OR this with 0, basically do nothing to it. So instead of exclusive ORing with the polynomial like we do up for these other cases, this is just all 0, so you're going to get the same result through, again dropping off this initial digit, this initial bit, because we don't care about it anymore. And the remainder is what's left here is 0, 1, 1, 0, and that is the CRC. So in this particular example, that is the CRC for that one byte going through the algorithm. So to look at it a different way, because that's a little long-winded, this is, believe it or not, the same mechanism, just written differently. And I've tried to draw it out here to make it a little more clear what's going on. And if you want to look in that, again, that document I referenced earlier, it's called, they call it the straightforward CRC implementation, or AKA non-direct. And this is the same algorithm as in the previous slide. Your initial value here is all ones binary 0xf, so we'll put that over here. So this is what we start with our register. So our register in this case has 4 bits, and we're starting with the initial value of all ones. The message is the same as before, the ASCII left square bracket characters, so that's these 8 bits right here, and our augmentation of these last 4 zeros. So the method you're going to do here to get the same result as before is you shift the bits left by 1, which is what this first line is doing here. And so you've got this 1 left over here. If the popped bit is a 1, you exclusive OR the register with the polynomial. So it's a 1. So the polynomial in this case was 1, 0, 0, 1, 1. We don't care about the leading one, so we're just going to stop talking about it now. You get the exclusive OR of that, and that gives you 1 and 0 is 1, 1 and 0 is 1, 1 and 1 is 0, 0 and 1 is 1. All the rest of these are the same. And then we continue with the same process. So we shift left. Again, the leading bit is a 1, or the popped out bit is a 1. Exclusive OR with the polynomial, you get the next sequence. Same thing again, exclusive OR with the polynomial. Here, as before, we got a case where the leading bit is a 0 that was popped out. So there's nothing to do there, so we just shift again. There's just nothing to do, so there's no reason to do null operation on the thing. So you just shift it out, keep working, and ultimately you get what's left in the register is the polynomial, so this is the remainder. And as you can see, this is 0, 1, 1, 0, same as in the previous slide. So one of the things the computer can do to make this a little bit better is, rather than running all these bits through every single time, is to store the pre-computed table values for all given bytes. So basically, you just ahead of time construct a table that has all of the table values for any given byte that would come through, so that you can just iterate through it byte by byte rather than bit by bit, and just use the lookup value instead. Here's kind of some C code that creates the table if you want to do that. You would just run this for each of your 0 through 255, in this case for a byte at a time, store that table, and then whenever you need to know what a table entry for one is, you just look it up and use it. So really, it's the same as before, only you just pre-compute everything ahead of time. So let's say I wanted to know what the table entry for decimal 91 is. And let's say for the 16-bit polynomial, we talked about on the second slide, 1021 hexadecimal. In this case, the index is this sequence in binary 0101, 1011, or 0x5b if you prefer hex, but this is just 91 represented as represented in binary. So if you go through the same sequence I had before of the index is the first 8 bits, and then you've got all the zeros on the end here for the other half of how you're generating this table entry. You take and instead this time it's not actually the message, but the index, you put it in here and you perform the same thing. You're going to shift it to the left, and then you're just going to bring in zeros here on the end. So just assume that you've got infinite zeros to pull in, to push in from the right-hand side. And again, if you pop out a 1, you're going to exclusive OR it with the polynomial. In this case, I've highlighted the bits here that are in yellow that are the actual polynomial bits. As you can see, the only ones here are the 1st, 6th, and 13th bits. So those are the ones that basically are going to flip. Any other bits are not actually going to do anything, so that's just what the yellow highlighting here is telling you. Those are the bits that flip. So in this case, they were all zeros in those 3 places, and now they're all 1s. Again, you repeat this procedure, and then in this case, when you exclusive OR with the polynomial for this particular one, there was a 1 here, exclusive OR that with 1, and so now this is now a 0. I just took out that step. But just to let you know, that's what this is doing if you're trying to figure out what this table is doing. But you keep repeating that until you've pushed out or popped out from the left-hand side all of the index's values, and what you're left with is the actual table entry for that index. So this would be what you would store in your table. So the index is 1 byte in this case, but the CRC table entry is actually 2 bytes. For an example of showing how this works, if you're going to use a table entry instead of doing it shifting 1 byte at a time, it's very similar. It's just you're going to work 1 byte at a time now instead of working 1 bit and shifting, and then 1 bit and then shifting and doing that 8 times. So the method you're doing here is you shift your register left 1 byte, use the rotated out value as an index into the table lookup, and then exclusive OR the table value back into the register, and then continue. So our initial value here is all 1s. The message in this case is the 0101, 1011, and then the augmentation bytes are all the zeros here. So we push everything over 1 byte. So now we've got 0xFF over here, the 0xFF here, this 0x5b is moved over here, and you're left with your 2 augmentation bytes over here. You perform the table lookup on 0xFF, and that results in these 2 bytes right here. And then you exclusive OR that with what you had, and now you have 2 new values in your register. Again, pop or shift to the left, pop out the far left value, perform a table lookup on this value again, exclusive OR, and then you repeat over and over and over again until you finally get your CRC. In this case, it's hexadecimal 0x27, 0x2. If you had more bytes, you would repeat this procedure again. You would keep doing the same thing for every byte in the sequence. Now, the other method that can be used is called a direct table algorithm, or in the Painless Guide to CRC Error Detection, this is called a slightly mangled table-driven implementation. The difference here is that we don't use augmentation bytes. So those do not get used at all. So the way this works is you rotate out the value and you exclusive OR that with the next message byte, and then use that for the table lookup and exclusive OR that table value back into the register. So it's a little different than before. So here we're starting with the same initial value register, 0xFF, 0xFF, and the message of 0x5b. No augmentation, so you do not have the zeros over here. So you shift to the left, you get the 0xF out, you pull in a 00 here for the new one here. You don't actually, so remember, we're not pulling the new message in this case. We're actually going to use that for the table lookup instead. So we bring the message over here and exclusive OR it with what was popped out instead, and that gives us this 0xA4 in this case. And then you do a table lookup for what 0xA4 is, which is this F5 and 6E, exclusive OR that with your previous register, and you have your new register. So that is your CRC, you're done. But if you're paying attention, what you might have noticed is this does not give the same result as the non-direct method. The non-direct method gave us 0x27, 0x02. This gives us 0A and 0x6E. So that's correct. They do not give the same result. So how can we make them give the same result? Just if you're interested, what you can do is change the initial value for the direct method to get the same result as what the non-direct is. So in this case, if I give it an initial value of 1D and 0F for the same message of 0x5b and perform the same calculations again, you get the CRC output of 0x27, 0x02, which is the same as the non-direct. So we can get the same result as the non-direct method without using augmentation. So, all right, so how'd I figure out that that was what the initial value is? All right, this is the easy one. The reverse is unfortunately quite a bit more confusing. But if you want to determine the equivalent direct method initial value based on the non-direct initial value, basically you just perform the non-direct table method on the non-direct initial value. So in this case, we just take the FF initial value that we had for the non-direct, just put the two augmentation bytes over here and operate on it using the non-direct method. And that's how we get the 0x1d, 0x0f if you want to follow through on the math. That's how you can convert from a non-direct initial value to the equivalent direct initial value. Doing the reverse, determining the equivalent non-direct initial value based on the direct initial value, this is a little more confusing. You're using the same polynomial for both methods. The short of it is you're going to perform a reversed non-direct method on the direct initial value. So in this case, the direct initial value is the 0x1d, 0x0f. So effectively, in order to get here, we had to pop out 2 bytes. So we don't know what they were, and in this case, we're going to be shifting everything to the right and doing everything in reverse. So what we have to do here is exclusive OR this register with a value such that the augmentation bytes pop back out as 0, because that's what we do know, is that the right-hand side has to be 0. So that's where this initial part comes from here. It's a little hard to follow without understanding what's going on, but you have to find the table entry that gives you this 0 byte for the augmentation, so that when you shift to the right, it gets pushed out and you end up with 2 bytes of augmentation that are all zeros. So that's what we do know, is it has to do that. So based on that, we know that we have to exclusive OR the register with some value to get zeros at least over in this right-hand part of the register. So the good news is that's easy, because the value, the right-hand byte of the table entry has to have the same as what the register is, because when you exclusive OR it, that's how you get all zeros. So when you do that, in this case, to get this 0x0f, the table entry for that is 0xe1, and that means that I have to put this E1 as the popped out byte over here, and then when you do the exclusive OR, you end up looking like this. So I know in order to get this first augmentation byte 0, the table entry here had to be this, and then I shift everything to the right. And then you're going to repeat the same thing again. So again, I have to get this right sequence to all zeros. So it has to be a table entry whose right half of the byte, or the right byte, is this. And that, in this case, is 0xFF. and I exclusive OR this 0xFF with the previous register, and then I get 0xFF, 0x00, shift to the right, and there, lo and behold, we have our 0xFF, 0xFF, and our 2 augmentation bytes. So what I left out here was how in the world did I determine what the table entry was for that had the right-hand byte being 0x0f? And is there only one solution to that? Well, the short answer is yes. There's only one answer here, and you can determine what the left-hand byte must be if you know the right-hand byte, at least for certain polynomials. This might not work for all polynomials, but for the polynomial 1021, this does work. So, more details into how the table gets built. So, the table entry for the index 0 exclusive OR y is the same as the table entry of x exclusive OR the table entry of y. So it's assuming x and y have the same length, as in, you know, they're a byte. In this case, the example is the polynomial 1021, and just to remember, this example is very specific to this polynomial. You would have to do the same workup for any other polynomial to determine what right now it looks like a mess down here is, for determining whether you even can determine what the left-hand set of bits is given the right-hand set. But to form this up, let's assume that the index is just 8 bits, and I've just labeled them as A, B, C, D, E, F, G, H. So each one of these is either a 0 or 1. I don't know what they are. So the table at any given index is going to be the A bit ANDed with the table entry for 128, the B with the 64, the C with the 32, the D bit with the table entry for 16, etc., 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 back to the H is 1. And this is just your basic binary buildup of, you know, this is H represents 1, G represents 2, 4, 8, 16, 32, 64, 128. That's all this is doing. All right, so if I write this out another way, what this is so H and the table for 1 is, the table entry for 1 is just this. So what this is the H bit ANDed with the polynomial itself. So as mentioned before, the particular bits that are getting set high or set for the polynomial are this entry right here, this entry right here, and this one right here. So that lines up with the polynomial bits. And those are the only bits that can be 1 if H is 1. If H is 0, then this entire thing is 0 and it's not doing anything. Same for the entry for the G bit, the F, E, D, C, B, A. So, the interesting thing to note here is really all of these are just like E, F, G, and H are just the polynomial shifted. But it changes once you get to this bit. So what's really happening here is you're getting to the point where this high bit here, what in this entry is on the E, you're shifting it out kind of off the end, so it really ends up kind of adding in again. If you write it out, you can see why this is, but this particular line, for instance, is the equivalent of the D bit ANDed with the polynomial shifted to the left 4, exclusive OR with the polynomial. And this repeats again to where you basically have 2 sets of polynomials. So if I write this another way, so let's say I exclusive OR all these together, you can just write it out like this just to make it a little more clean. So you've got sequences of the message, or the index, A, B, C, D, E, F, G, H, kind of in different places throughout the final table value. All right, so the last interesting thing I'll go into here is what I used for computing the non-direct initial value based on the direct initial value. I kind of skipped over the details here a couple of slides ago, but this is really what you can do to figure the table entry out. You can figure out for that particular polynomial what the table entry is at a given index if you only know the last 8 bits. It's actually perfectly deterministic what the first 8 bits must be in order for that to happen. If you have other polynomials, you might have to work it out to see if the same is true in those particular cases. It might be that for other polynomials you need to know other bits, but in this case there's sufficient information in the last 8 bits to determine what the first 8 are. So how that works is, again, you have the table entry at the index given here, again, where the index is the byte A, B, C, D, E, F, G, H are the bits. What you can see here is you've got this lone D in a column all by itself, exclusive ORed with all zeros. So really what this means is this particular bit is the D bit. Therefore, in this example of a table entry ending in 00001111 or 0F hexadecimal, the D bit must be 0. And if you continue the same logic, D is 0, H exclusive OR D is 1, therefore H must be 1. And you continue this down and compute the rest of them. For this particular entry, you can determine that the index that satisfies this condition of these last 8 bits, in this case, is 111000001, or 0xe1 hexadecimal. And of course, once you know that, you also know the first 8 bits. And of course, this also, as I kind of alluded to just a few seconds ago, knowing the last 8 bits, there's only one solution for the first 8 bits for the particular polynomial I'm talking about here. So now we've finally gotten the background out of the way, and at this point should have a basic understanding of how the CRC routines work. What exactly is the PCjr doing? Well, before we go into the details, just in brief, what it is using the CRC 16 or CRC CCITT algorithm. And this is, again, as I said previously, used by the PCjr cartridge routine. And so what it's doing is it's running the CRC code on the bytes of the cartridge, including the header information and the CRC at the end. And so the end result should be 0000, and that's how it knows that the cartridge most likely does not have any bad data in it. Or just more specifically that it is a valid cartridge. And you can find the algorithm that I'm about to go over here in the PCjr Technical Reference Manual, page A106. And specifically the polynomial is the one I've been using as an example, x to the 16, x to the 12, x to the 5 plus 1, or 0x1021. It does use an initial value of FFFF, and it is using the direct method. All right, so for those of you who are still with me here, we are finally going to start looking at the PCjr implementation. So this is the BIOS routine for the CRC check out of the PCjr Technical Reference Manual, page A106, starting at address FE71. This is what the assembly code looks like. And on the right here I have some C++ version, if you will, of the same code that does the same thing. If you're like me and this is the language you know, I'm still learning assembly, so I figured it out for this example, but I'm by no means an expert. But this code does basically the same thing as what this does, and I've commented by it for what each line is actually doing. You can, at the end of this, you can see I'll have a link to my GitHub where I have a copy of this code, or a usable version of it you can use to calculate a CRC if you want to in C++. So what exactly is the PCjr routine doing? The interesting thing here is you can see there is, or maybe you can't if you're not as familiar, but there is no table buildup in this routine at all. It does not run through all characters or all byte combinations and create a table entry for each. And the loop here that it does for to the CRC1 label from down FE95 to FE7B only loops over each byte. The LODSB is actually where it pulls in the byte, and if that's actually on the cartridge, or the actual data or message, as I've been calling it so far. And it only loops through one time for each byte. So at first, this doesn't really look like any of the methods I've discussed. So what it's actually doing, the PCjr is performing a direct table method, but there is no table created. The good news is here it's saving memory by not having to pre-compute 256 values times 2 bytes table entries at the expense of compute time. So it doesn't have to store these in memory, but of course it's going to take it a little longer to go through this routine, but it only does it at startup and only if you have a cartridge in, so it's not really that big a deal. So, starting from the beginning, and I've got the addresses kind of here on each bullet and the instruction that's on it. You can cross-reference it here with the highlighted section, but in this case, I'm only going to go through the initial pass-through on this code. So I've got the AX and DX registers here. The working register for the CRC is actually the DX. So the first thing it does is it clears out the high bits on AX, and then the low bits are whatever was in there before. And then the DX register, for the first pass at least, is all ones, or the FFFF sequence. On subsequent runs, this DX will just be whatever was remaining from the previous byte calculation of the CRC. On the second line, we load in the next byte from the cartridge, so we add in the A, B, C, D, E, F, G, H bits. So these are not hexadecimal. Just remember, these are just what I'm calling the bits, and they're either just 0 or 1. And so this is what your registers look like. And then we do an exclusive OR with DH and AL. So DX turns into what it was before, exclusive ORed with the AL values, and moved up to the high bits and exclusive ORed with what DX was. So DX is really the combination of these two. The reason I show this is so you can see how it actually builds it up. The next one is to move the DX register's high bits into the AL's low. So we get that here. We take the high, which is the one exclusive ORed with A, B, C, D, E, F, G, H, and move it into AL. So now AL is now that part of the sequence, and it does not touch the high bit, so that's what was left over from before. Continuing, this is where we left off. If you keep going, the next one is to ROL, which is effectively a bit shift left or rotate left. So we're going to, CL happens to be 4 in this case, so we're going to shift the AX register left 4 bits. So that's all that happens there. And then we do an exclusive OR with AX and DX and store the result in DX, and you get what I have down here. If you continue, the next one is to shift left 1 bit on the AX register and exchange the DH and DL half of the register. So it's swapping ends. And continuing, we do exclusive OR with the DX AX register, store the results in DX, and you end up with this. And then again, a rotate right on AX, so this one gets shifted back 4 bits to the right again. So AX now looks like this. And then we do an AND with the low bits in the AX register with the 1110 masking. So basically it's masking out some of the values to cut this down to just A, B, C, D. So the E, F, G, H bits have been stripped out. And then we do an exclusive OR with DX and AX. And we end up with now DX, of course, getting even larger. So, I mean, obviously in memory, this is still just 16 bits. We get down to FE90. You've got another rotate right. So bit shift right on AX by 1 bit. And then an exclusive OR of DH and AL. So that takes the ABCD, puts it into the high, or for exclusive ORing with the DX register, and we now get this sequence. And if we clean that up, what you get is this sequence of bits at the top, and then this sequence of all the bits that are the A, B, C, D, E, F, G, H message or byte, if you will, that came in from the cartridge. So if you recall from before, I showed that the table at a particular index labeled A, B, C, D, E, F, G, H equals this. Well, guess what that is? That's what all this is. So it's building up on the fly the table entry at that particular index. So the only thing that's left is it's this bit sequence exclusive ORed with the table entry there. So what is this bit sequence? Well, if you recall, the direct method calls for a table lookup of the exclusive OR of the rotated out value with the non-augmented message. So the rotated out value, or the high bits of the initial value in this case, which is 0xFF, and the non-augmented message is the A, B, C, D, E, F, G, H bits. So the table at index 0xFF, which is the popped out bits, exclusive ORed with the message bytes, excuse me, equals the table at 0xFF exclusive ORed with the table at ABCDFGH. Then the table value is exclusive ORed with the register. So in the end, what that means is you're doing the table entry at index FF, exclusive ORed with the table entry at ABCDEFGH, exclusive ORed with the register after the shift, which is 0xFF00. So if we write that out, this is the FF00, this is the table at 0xFF, which you can use the previous method to determine what that is, and you end up with this bit sequence, which is what we saw in the previous slide, is this this value that the table at the index is exclusive ORed with. So that's how that works. Is really that's what it's doing. On the right here, I kind of have the buildup of the same kind of buildup as I've shown before. All right, so in conclusion, that's what the PCjr is doing. It was quite interesting to go through this, from starting off on this and having no idea how a CRC algorithm worked. It's been a long time since I've worked with anything like this. And it threw me for a loop, if you will, pardon the pun, but just because the PCjr routine wasn't doing anything that looked like any of the CRC algorithm information I saw, it took me a little while to determine exactly what it was doing, but hopefully this is of interest to someone and maybe helps you understand what it's doing a little bit, or at least you just find it interesting to understand like I did. So that's probably way more than you ever wanted to know about the CRC algorithm used on the PCjr cartridges. Hopefully this would help somebody, if you've got any other CRC algorithm that's similar, that's maybe doing something similar, possibly with a different polynomial, you can figure out what it's doing or even do your own implementation based on that. And I will put up on my GitHub, I will put up a copy of the Painless Guide to CRC error detecting algorithms, only because I had a little bit of a hard time finding it, and it is a good document to read through, just so it doesn't get lost. And also I've got my C++ implementation on there, so feel free to go check it out if you want to understand what it's doing in C++ if you don't understand assembly. And I've got a link to my GitHub here, but you can also find it in the video description. So thanks everybody for watching. I hope you found this interesting, and hope to have another video when I can manage it. But let me know if you have any questions or comments in the comment section, and feel free to like and subscribe. Thanks very much. Bye.